All right. So like before, if you have been here, what I do is I use a Jupyter notebook and I put it on Google Colab because Google Colab has got a very good environment where there's a whole lot of functions already on the Google servers. So there's quite a lot of Python already pre-installed, and it's quite a nicely defined environment. So anyone can actually use it for themselves, and it makes it much easier. Actually, there's probably a few more people coming in. Okay, cool. So this Jupyter notebooks on Colab are really a great idea. The other thing that I really love using it for is back in the days when I sat in cafes a lot and I actually programmed from my laptop and I had to run some quite intense simulations. Colab was much better because it just simply didn't drain my laptop battery quite so much, which is a big advantage sometimes when you're really, when you spend a lot of time in cafes and you really need the battery for quite a while. So that was helpful. Now, not everything is installed on Google Colab, and today I just get the data from Yahoo Finance, and we've got a Y Finance package, which is fantastic for that. So all you have to do is go pip install Y Finance. It installs that on the Colab environment. And then here I've got a blur of code. And basically what this does is it installs TA-Lib. And TA-Lib is just a technical analysis library. So it gives us a lot of indicators and technical analysis tools out of the box, which is extremely handy. So you can install this directly onto Google Colab as well, which is fun. I've already done this here. It takes only a few seconds to do, and off we go. So that's extremely helpful. Then I just installed a few packages. Now we probably won't use all of them. So the PCA, maybe not the minimization, but we've got pandas, matplotlib, numpy, and Y Finance, of course, and TA-Lib, which I imported up here. And then that's really all we need to set up. Now, the other thing that I've done here is I got a lot of stock tickers from the basically the complete S&P 500. Okay, there's another person coming in. So what I did was I just got all these tickers from the S&P 500. And for today's demonstration, I just used the first, whatever it is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, like 15, about 15 tickers. So they're just selected effectively because they start with the letter A, and there's one just right at the beginning called MMM. But that, I didn't really make it. It's really for demonstration, so I didn't choose anything specific. What I really want to show today is the process of factor modeling, and then if you want, of course, you can take all the tickers, and then what happens, of course, is the functions will run a little bit longer, and you can just do the same thing. But with what I'm going to show you today, hopefully you will actually find that comparatively you can run your backtests blistering fast. Okay, so the next thing I'll do here is I download all the stocks. Still people coming in. I download all the stocks, so I just go Y after download, and I start 2007 just to grab the 2008 correction as well, which is really helpful because it's always good to test on some. We've had two big corrections, 2008 and 2020, so it's nice to have the backtest go through two big corrections. It's always a nice thing. And so once I've done this, I've already downloaded them. Actually, only takes a few seconds for those 14 instruments. And then I extract a few things. Here I extract the adjusted close prices. And I just go DF, which is the data frame that is returned, adjusted close. Then I turn those adjusted close prices into returns. So I go adjusted.pct change. And what I do here, fill NA, basically means when I have NaNs, not a number, I just fill them with zeros. Sometimes that happens. In fact, this is not supposed to happen here. We don't want to fill close prices with zeros. What we can do, however, is we can fill percentage changes with zeros. And then there's sometimes some infinites as well when you calculate your returns, because you have it divided by 0. So you want to make sure also that you get rid of them, because otherwise it will screw over your calculations. So let's just run this again. Okay. Oh, I haven't, for some reason, it hasn't actually run yet. Now it looks like I need to rerun it again. Okay, so I'll do this now before I get into any trouble. Okay, so this runs. We do this, we create the data frame here. And then we create our returns, which is that. Now let's have a quick look at the data frame. So you can see here, we've got all our instruments, and then we've got a multi-level index for those of you who are familiar with pandas. So we've got the stock tickers on one index level, and then we've got our close prices, and then open, high, low, and so forth on the second level of the index. This is just how we get our data frame returned from Y-Finance, and that's a really handy one to use. So I'm going to continue using it. Okay, so now let's get started. Now the first thing we want to do is create what we call factors. And what is a factor? A factor is basically a piece of data which is somehow correlated to the forward returns of a stock. So what that means is we get a value from something we calculate, and that has some sort of predictive property for the stock returns in the next period. So let's just say we get a value of 1, and then that predicts us, oh, we got a positive return in the next period. Or we got a value of -1, it means we got a negative predicted value for the next period. Now that's all good and well. Unfortunately, those correlations are generally really, really low. So there's very few of those correlations that actually work particularly well as predictors on their own. And in a sense, it's a bit like machine learning. You've got, for example, in machine learning, you've got a whole lot of weak predictors, but what you can do is you can put them together and then feed your machine learning system with them, and you might end up with stronger predictors. Now, one of the really important things here is these predictors should be relatively uncorrelated to each other, because if they're highly correlated, it just means that you feed every factor that you use does more or less the same thing, and then you may just as well feed one factor in your model, and there's nothing gained from that. So we want to find some sort of predictive values. Now today, I'm not going around and working out what the predictive values is. So what I'll do is I'll just take a bunch of technical indicators. I'll analyze them a little bit and see whether they have some predictive value. And then what I do is I take those indicators and their predictiveness, and I build a factor model around it. So I basically create this factor model from those more or less random indicators that I picked, and then we'll see how good this might be. And then what you see is how I go through the process of building a factor model effectively from scratch. Now, there are, of course, quite a few software packages out there that can build factor models for you. Problem is they're usually very institutional grade, first of all, and therefore they're pretty expensive. You know, you pay per year upwards of 50K for those packages, which is, you know, mostly not so good for the average guy who works on their own. And the other problem is you don't really know with those factor models that you can buy what's actually under the hood. So you might actually run them and apply them, but you don't know what the developer really built there. And sometimes that can be great. And if you trust it, it's really good. Like a friend of mine, you know, really trusts their horoscope for their daily actions, which is also great, you know, like if it works for you, that's fine. But it's sometimes really a good idea to actually know what you do. And the other thing is, if you build it yourself, you can also really control and tailor what you're doing. You know, you can take whatever you want, you can combine it any way, shape or form you like, and you're not limited to a specific way of doing things, which most of these packages obviously make you do in the name of user friendliness. And of course, that's great, but you know, when you do this, you basically get the same results that everyone else gets. And that's probably also one of the reasons why a lot of fund management institutions generally are very highly correlated with each other. So if you look at, for example, you know, a lot of the equities hedge funds, you know, that they're fairly correlated with each other and so on. So if you want to step outside, look outside the box a little bit, it's always a good idea to then go and maybe start building your own stuff, or at least understanding what this does. And this is what we're going to do today. Cool. So let's just start with some indicator that I just picked. I just, you know, before I started this, I thought, oh, okay, you know, like, let's just see some straightforward ones. And so the first one that I'm looking at is called rate of change. So what I can do is to call it, I just go TA-Lib, and then we've got ROC, which is our rate of change. And if we click this, we can actually see what inputs we need. So we need a input value or input array of values, and we need a time period. So that's fairly easy to do. Now, what we want to do is we want to apply this to our returns. So we want to apply this to the data that we have, and so, you know, we hope that the rate of change is somewhat predictive. So in order to figure that out, we have to first apply it to all the different stock prices that we have. And now, in order to do this, we could just run it through a loop and then apply it like one by one. But of course, as we are a little bit smarter in programming, we might do a little trick, and we use effectively the pandas library for that. So remember, we had this ADJ for our adjusted close prices, and then we can use a function called transform. And what we do is in transform, we use an anonymous function called lambda. So it's a lambda function. And it's basically just, instead of using def or define as you normally create a function in Python, we use what's called lambda, and we can just define the function in line here. It's called an anonymous function. And then, for example, we can put this in X, and then we put in a look back window. Okay, so what this basically does is it looks at each of the columns, and this is X, you know, column X. Then it applies this rate of change indicator, and it applies it with a rolling window of 10. And so we can just run this, and then here we get our rate of change values for each time step and each of these equities. Now, at the beginning, we've always got a few nans. That's just simply before we get our rolling window filled, before we get 10 entries, it doesn't actually calculate, it just returns an NaN. So we could, for example, call this ROC equals this. Now, this is just our rate of change indicator. Now, now we want to kind of know whether there is some sort of predictiveness in that indicator. And how can we do this? Basically, what we want to do is we want to take the indicator values and then correlate those indicator values with the forward returns. Okay, how can we do this? Now there's a few tricks that we could do. So for example, we can go ROC dot, and then there's this function in pandas called core width. And so what this does is it doesn't give us just a correlation of one column with one stock and one indicator. It just does the whole matrix of correlations all in one go. And so we say, well, our rate of change indicator, we correlate it with our returns, which we call reds up here. And let's click this away. And I told you that we actually need to use forward returns. Now, if we just put it in as it is, there is a problem, because what we have is we have the value of our indicator, and then the return is actually calculated at the same time, but it's calculated from the current or from the previous time step to the current time step. And so in order to get the exact value for the forward return, so for the return the next day, so that we can actually see if it's predictive, we can then, we need to shift the returns to the left. So if we shift them to the left, then we get the future return aligned with the indicator value of that day. Okay, so let's just do this. Shift, and then to go to the left, -1. Now, one thing we also need to do is here with this correlation, we need to define axes equals 0, which means we do this on a column-wise basis. So we've got the columns with our indicators and the columns with our stock returns, and we correlate them together. We shift one of the columns. Why do we do this so complicated? Simply because if we would actually do this all with loops, it would run approximately 20 to 30 times slower than when we do it in that way. And so it's a little bit of a head thing, you know, it's like, oh, you have to really think about how do you do this. But once you figured it out, it's actually really nice. And so if we run this, for example, let's just do that. We can actually see here, these are all the different correlations that we have. So they're all like correlation coefficients. And you look at this and you go, wow, this is, these correlations are really low. You know, an ideal correlation is 1 or -1. And these are usually 0.05 here, 0.02, 0.03, 0.07. But the interesting thing is they're actually fairly reasonable. So in terms of factor modeling, we do not expect the correlation values to be large at all. It's actually almost impossible to get good factors with anything above, say, 0.1 or 0.2. It's quite rare. I mean, it does happen, and if you build a good model, sometimes you find these things. But generally, with those typical factor models, a reasonable correlation coefficient is actually around 0.025. So anything above 0.025 or -0.025 is actually quite good. So if you see that, that's the sort of stuff that you're looking for. And then what we're doing is we're combining them, and you know, given that they are not correlated with each other or not too correlated with each other, we can say, oh, we can build a nice model out of this. Now have a look. Let's have a look what the average of this is. The average correlation value, it's actually 0.038 or -0.038. So that's actually okay. So, you know, we can say, hey, you know, this is not too bad a predictor for our models. Now, so we're quite happy with that. Now what we've done here is we've actually took, or we looked at the correlations in a column-wise way. So when we look at correlations, we say, okay, these are our returns at a certain point, and these are the columns aligned to this. But there's also another type of correlation, which is called a cross-sectional correlation. So instead of doing it column-wise, we can actually do this row-wise as well. And so what we're looking at each and every time step, we look at all the different stocks at one time step, and then we do a correlation between the values for each stock and the forward returns for each stock at a single time step. And lucky enough, what we've built here makes it already really, really easy for us to do a cross-sectional correlation rather than a column-wise correlation. And all we have to do is just redefine the axes. And we go axis equals 1. And we got a cross-sectional correlation. And you can see here, that's actually a lot lower. That's minus 0.009. So it's actually not that great. So if we wanted to use this model or this factor specifically, we have to make sure we're not applying it to a cross-sectional correlation, but rather to a column-wise correlation. There is very philosophical debates about which one is better. I can't really tell you. I just know what I know, and everyone has their own understanding of how this works. Now, in our case, maybe let's just go with the column-wise correlation for now, and we find better results that way. But you know, this is just so you understand how this works. Now, again, you have to think a little bit out of the box in terms of matrices and vectors. So column-wise is really along the time axis, and row-wise is really along the axis of the equities. So that's how you understand it. If you do a row, you do something along each equity or each different ticker. If you do it along the column, which is axis equals 0, you do it along the time axis. Okay, now this is a rate of change, and it actually just takes a simple input value, x, which is our adjusted close prices. Now, if we wanted to use other indicators, unfortunately, things are a little bit more complicated. So for example, if we use something like the Aroon Oscillator, which is another indicator which I picked. So we take the Aroon Oscillator. You can see that instead of just close prices, we actually need high and low values, as well as a time period. Now, that makes our calculation a bit more complex, because we cannot simply use this beautiful transform function anymore. So we have to figure out a bit of a trick to get around this. And one way to do it is just to simply run a what you call list comprehension on a pandas data frame. Now, this is a little bit of a loop involved here, so we can't actually do this purely from a vectorized perspective. So it will take a little bit longer than what we've done previously with transform. But unfortunately, in order to get it purely vectorized, we would have to build a lot more complexity into it. And I really want to spare you from this, as this is already complicated enough. Okay, so the first thing we want to do is create a what you call a list comprehension. And we do this actually not as a list, but as a dictionary. So pandas, Python dictionaries. And there's still people coming in. Wow. Okay, so one thing we do is we say, we create this as our key, and then we create the indicator as our value. And then we go for sim in sims. Now, as you might remember, sims is just a list of our stock tickers here. So we've got a list that we split of our stock tickers. So we go through all the stock tickers, and then what we need to put in here is df, and you remember we needed a high and a low price. So we go df.high, and then we go sim. Then we do a df.low. So that's our low price. And then our sim, which is also the symbol. And then we need a time period. Let's just put in 10. So, or actually 5. So that is what creates this list comprehension dictionary, and it calculates all the different oscillator values for all the different symbols that we have. So if we run this, we can see it's just this dictionary. Now, in order to make this more manageable, what we can actually do is then wrap this into a pandas data frame. So we go pandas data frame, and this basically just puts it into a nice pandas data frame, and then we can actually use it for processing it further, which is really great. So you can see here the dates. These are the different tickers, and then these are the different values of our oscillator. And so this is really fantastic. We call this Aroon, makes it easy. Okay, now what I wanted to do is just create 2 more of these just for an example. So I picked another one which is called CCI, and all I do is I just copy and paste this, and I go CCI equals this, and then here I can just put in CCI. Now the CCI takes slightly different values, and I forgot which they were. So it actually takes high, low, and close. So all I have to do is add a close value to it. So I go df dot close sum, and then I'll pick another period for that here, 20. Okay, and then a final one. So here, oops, a final one. There is another indicator that we can use. It's called balance of power, BOP. So if you want to know exactly what they're doing, maybe just look them up. In Investopedia, they're all explained really beautifully, and you can really play with them. Now, personally, I'm more interested in the outputs and what they deliver us, and that makes it so much easier for me to understand. So I just create this indicator here, and it's called BOP. And BOP uses actually open, high, low, and close values. So I have to add another one, df.open, and then sum. Here we go. And actually doesn't take any period. Okay, so now we've got 4 different indicators, and we'd be interested to know whether they are predictive or not. So first of all, we need to create them, and let's run this and hope we're not going to get an error. Okay, so this ran. Let's just double check whether this is actually working. Oh yeah, there you go. BOP is working, gives us a lot of values. So great, we have now a bunch of indicators. Now the next thing we want to do is actually see, first of all, how correlated they are. We could also look at how predictive they are. Now we've already, in a sense, done a little bit of this up here. So I've already shown you how to calculate predictiveness with core width. So you could effectively do exactly the same with the other indicators. So instead of ROC, you just go Aroon.CoreWidth, and then do the same here. So we could just actually do this just for demonstration. Okay, so we got this value here. So it's not quite so good. It's minus 0.021. So it's just about okay, but not fantastic. So we're not so sure about the Aroon oscillator, but what I'm doing today is just plug them all into a model and see what we get out of it. So this is really the key for today. How do we build a factor model? How can we put it together and then understand what it's doing?